Welcome. This video is going to be talking about integrated rate laws and how we can use them. So first of all, overview, analyzing kinetics using data. So we know that we can describe the kinetics of a reaction using something called a rate law. And the rate law shows the relationship between the rate of a reaction and the concentration of the reactants raised to some exponent that is called the reaction order. It's also affected by constant K, and the reaction mechanism is what determines the rate law. So a rate law looks a little bit something like this. Rate equals some constant K times the concentration of the reactants to some exponent. And that's for however many reactants you have. There are two ways in which you can experimentally determine the reaction order of a reaction. One of them we've already done, comparing molarity versus rate. And this is what we did on the most recent lab. We did a baseline reaction, determined the initial rate of that reaction, and then we changed variables one at a time. So we said, what happens if we double concentration of A? What does that do to the rate? What if you double the concentration of B? So that is one way to determine the rate law. Another way to determine the rate law, which is what we will look at today, is to observe a single reaction over time. So it's really important when you're trying to do your problem solving, ask yourself, what type of data am I given? Is it molarity versus rate or molarity versus time? Here's a picture showing you what that looks like. So molarity versus rate data is going to look something like this. Over here on the left, usually in a table format, you can see we've got varying molarities and varying rates. Molarity versus time data might be given in a data table, or you might be given it graphically. So just make sure you're reading your axes or your column headers in your data table carefully. So if you have data that is, so you have some numbers relating to molarity versus time, that means you want to be using something called the integrated rate laws. So if you pause right now and look on your equation sheet, you will see this right here. There is a kinetics section. It is small. There are only 3 equations on it. And these equations are known as the integrated rate laws. And yes, that's integral like in calculus. And no, you don't have to be able to do calculus in here. Just realize that, somebody else did some math that converted our rate laws into these equations right here. And these equations are useful because they relate molarity, concentration, and time. So use these when you've got concentration versus time data. Also right here while we're on this page, reading in the textbook is on page 607 to 614 if you want to refer to that. So let's do a quick overview of the math. Again, no, we're not going to get into calculus, but just realize, yep, someone did some math and came up with these equations right here. So let's think about how they're used. So if you are a first order reaction, which means, remember what that means is that, your rate law equals K times A, that the exponent right there is a 1. Then if you do the calculus here, if you integrate this equation, sorry, my 1 looks like a 2 kind of, okay, that is a 1. If you integrate this equation, you'll end up with this down here. Okay. The natural log of the concentration at time t minus the natural log of my initial concentration equals negative K times t. This is the rate constant K. It's the same K as we dealt with up here. T is time. So that is an equation. So notice, again, this is the equation that's on your equation sheet. Since we have an equation, we could plug in some numbers and solve for stuff. So like if someone told you what the initial concentration was, and you know amount of time that has passed, and you know the rate constant, then you could calculate the concentration at time t. Or if you know the change in concentration over time, you can calculate the rate constant K, or you could calculate how much time it takes to get from a certain concentration to another concentration if you know the rate constant. So you can do some math here. You can plug in some numbers and solve. The other thing we can do is we can use this graphically. We can do some graphical interpretations. So if you take this top equation and you rearrange it, you can get it to kind of look like the equation for a line. Y equals mx plus b. And why that's significant is that tells us that the relationship between, so basically y is the natural log of the concentration and x is time. So if we were to plot the natural log of concentration versus time, we should see a linear graph. So if the reaction is first order, a plot of natural log versus time will be linear. So here's an example of what that might look like. Notice that for this line, the slope of the line is going to be negative k, because going back here to this page, you see how m, our slope, is negative k. Okay, what if you're second order? So second order means this exponent right here is a 2. If you do some calculus here, you end up with this equation, which again is on your equation sheet. You don't need to memorize it. And here again, we can see some ways in which we might do some math here. So you might know, if you know the initial molarity at time 0, if you know how much time has passed, you know the rate constant, you could determine what the new molarity would be after that much time has passed. You could determine the rate constant or determine how much time has passed, just depending on what you're given. And these values are both the inverse. One other note here, if you think about units, 1 over A is 1 over molarity, which can also be written as m minus 1. So these are the units here when you're talking about 1 over A. If you rearrange this to solve for your rate constant, you're going to see it looks a little bit something like this. It's 1 over molarity divided by time. So let's say that our time was measured in seconds. You would end up with 1 over molarity seconds, which can be written as m minus 1 s minus 1. And that reminds me, let's go back to my first order rate law. In this example, if you're wondering what the units are here, whenever you take the log or the natural log of something, it is unitless. Another example of this would be pH. So you see something has a pH of 5, there are no units there. And that's because the pH is the log of the concentration. So whenever logs and natural logs are going to be unitless numbers. Okay, so here's our second order integrated rate law. And again, we can think of it as a graph. So you can rearrange this equation to have it look like y equals mx plus b. In this case, your y value is the inverse of the concentration, and the x value is time, which means if you plot the inverse of the concentration versus time, you are going to get a linear graph if your reaction is second order. So it would look like this. Here's a summary. We haven't talked about 0th order yet. You will not run into that as frequently, but if the reaction were 0th order, then the rate will not be affected by the concentration, which means the concentration versus time is going to be linear. So like throughout the whole reaction, the concentration versus time is going to be the same. If the reaction is first order, the natural log of the concentration versus time will be linear. If it is second order, then the inverse of the concentration versus time will be linear. And I drew what this looks like graphically. These are rough sketches of the curves. But what's important to notice is that if a reactant is 0 order, then the concentration versus time will be linear. So I'm going to circle this one. If it is first order, the natural log versus time will be linear. If it is second order, the inverse of the concentration versus time will be linear. So for any given scenario, only one of these three graphs is going to be linear. The graph which is linear is going to indicate the reaction order. And this is one of the most common applications of the integrated rate laws that you will see. So again, looking back to where this is on the equation sheet, it is in your kinetics section. These equations are given, but they are not labeled, so you do need to remember that the first equation goes with a first order reaction, the second equation goes with a second order reaction. Remember, we're talking about order that has to do with the exponent that shows up in the rate law. And the types of problems you want to be able to solve with this equation, you want to, just like we saw 2 slides ago, to be able to interpret graphs. So based on some data, you want to be able to look at that data and determine whether it's 0, first, or second order. So you're looking at which graph versus time is linear. And you also want to be able to use that rate law equation and given values to do some calculations. So depending on what you're given, you might calculate for time, calculate K, or calculate concentration. So you're just doing some math, plugging and chugging. So let's do a quick sample problem here. So if you look here, this is our equation. We have just one reactant. So let's write out the base of our rate law here. So rate equals K times NO2 to some exponent. We're going to try and figure out what the exponent is. So using the data in the graphs below, we want to determine the rate law of the reaction. So I've got three graphs here: natural log versus time, concentration versus time, and the inverse of the concentration versus time. And I want to ask myself which of these graphs is linear. It looks like in this case, this graph right here is the linear one. And if the inverse of the concentration versus time is linear, let's go back to my other slide to reference here. Okay, if the inverse versus concentration as time is linear, that means it's second order for that reactant. And the way I remember is I look on my equation sheet and I'd say, okay, natural log is the first equation, inverse is the second equation. So if the inverse is linear, the second equation is second order, so A must be second order. Okay, so since this is linear, that tells me that it is second order, which means this right here is a 2. So now I've got my rate law. And then I want to find the value of the rate constant. And normally, like what we've done in the past with this is we've plugged in data for rate and molarity and solved for K. So we've said, okay, K equals rate divided by NO2 squared. And this equation works, it's just we don't have any rate data. We're only given molarity versus time data. So I can't use this equation in this scenario. But remember, I have a new equation that I can use now. It's that integrated rate law. So whenever you have concentration and time data, you should use your integrated rate law. And your integrated rate law is right here on your equation sheet, this one right here. So I'm going to look at my data from the data table and I'm going to plug some values into this equation. I know the values of the molarity at various points in time, and I can plug in for how much time has passed, and I'll be able to rearrange and solve for K. So let's take a look at what that would look like. Whoops, okay. We'll plug this in real quick. So I could say 1 over A sub T, that is the concentration at some time T. Let's use this. Let's call this time T, and this is my time 0. So 1 over A sub T is 1 over 0.015 molar minus 1 over the concentration at time 0 equals K times T, which is the amount of time that has passed, which is 100 seconds. I can never remember if the K is negative. No, I think the K is positive here. Okay, so here's my equation, and I'm going to rearrange and solve for K. So K equals 1 over 0.015 minus 1 over 0.07, and then the units on the top are 1 over molarity, and you're going to divide it by 100 seconds. And when you plug that in your calculator, you should get something around 0.52, and the units are 1 over molarity second, or you could write that as 0.52 m minus 1 s minus 1. So you get somewhere between 0.52 and 0.53. Okay. So please email me if you have any other questions on this.